Okay, good evening, everyone. Welcome to TIZED's course on design and analysis of sustainable urban neighborhoods for energy, water, and food independence. I'm Jeff Brook-Thorson, the Associate Director of TIZED, which is the Trotchi Institute for Sustainability in Engineering and Design. I'm also the Panda Faculty Scholar in Sustainable Engineering Design here at McGill and an Associate Professor in the Department of Mechanical Engineering. The event is being sponsored by Fondation 3E, and I'd like to give a warm welcome to the President of the Fondation, Mr. Michel Gélina, who's with us here today. They are sponsoring this course and are really interested in improving energy literacy, which is an important topic for improving sustainable engineering and this transition to clean energy that we're looking to find. And that really will come about through a highly trained workforce, such as the students that are in the course today. They also promote the reduction of energy consumption in the urban environment, which will require collaboration between engineers, architects, and urban planners. And this course brings all of those types of students together, and we're going to hear about those interactions today. And so the mix of those students in this course is an example of this type of collaborative effort.
Now, before we begin with the student presentations, I just want to make a few very brief but important points about the course. Number one, this course is a thought experiment. There is no real-world client because we don't want one. The course mustn't be constrained in imagination and creativity with constraints that a real-world client would bring. So, as Jeff mentioned, 4 student groups will, have examined 3 existing suburban neighborhoods on the island of Montreal, with the task of retrofitting them to become totally autonomous in terms of energy, food, and water in the operational needs of the communities. So now, as you watch the student presentations, keep in mind that they were asked to do 3 things. Number one, they were asked to articulate a clear and powerful vision that would guide them throughout their design exercise. They were also asked to develop a clear design strategy for achieving energy, food, and water autonomy. And very importantly, they were asked to validate their design strategies by using quantitative models, tools such as Red Screen, such as Hot 2000, Homer Pro, etc., and spreadsheet tools that they built for themselves.
Dear students, friends, faculty, it's always a pleasure to be here because this is where the rubber hits the road. We may have an idea, we may have this view that energy literacy and energy numeracy matters a lot, but it's only when we see you that we see whether our ideas make sense or not. I would like to echo the words of Jeffrey and the words of Sevag. Yes, it is what the university is all about, that is exploring matters, concepts, and ideas that may be at the fringe or not mainstream or old-fashioned at times, like reintroducing rail and electrified transit in our neighborhoods. But I'm also very pleased to see that there are students from so many different walks of life.
So the vision that we developed is right here. I'll let you read it. So the main points of this, though, are that we want an autonomous site, clearly. We want to make a lot of connections between our different systems. We want a variety of options so that there is more resilience and sustainability. And then we also want to make sure that there's an interactive lifestyle for our residents to build a more community feel. So over here, you can see this is a polycultural forest. Next to it is going to be a farm space for animals to graze, so some goats and chickens. This is an agricultural space for some outdoor crops. The center right here is a community and recreation area that's really important for us to encourage healthy and active lifestyles. So we've actually kept most of the features of the original neighborhood, like the sports fields. And then up in the corner is our residential area.
To build a completely autonomous system, which also means not connected to the grid in terms of energy, is not an easy task at all. But I think it's actually a great opportunity to think of a design with these constraints because it forces us to to make our system really efficient. The rest of the consumption is divided into 4 categories, which are domestic appliances, domestic hot water equipment, and plug loads. To make a really efficient system, we took care of separating the primary energy needs, so in terms of thermal loads, which are in red here, and the secondary energy need, which is mainly electric loads, in blue.
And the solution that we've designed to retrofit our neighborhood will not only reach our energy goals, but also be the solution to many other problems such as social and economic problems that the region may face by reuniting the people with the land that provides them with their natural resources and by eliminating any economic struggles that they may be facing by allowing them to be completely dependent on the land that they're harvesting from.
Now we will look more at the energy strategy, and we have 3 main tactics to achieve energy autonomy. The first being reduction of the consumption of the community, then finding diversified sources of renewable energy, and finally managing the peak demand. So we first have the wind farm and the anaerobic digester. These are connected to a distant grid to then feed the households and the greenhouses. Those, however, have PV panels installed on the roof so that energy comes from there as well. And both the households and greenhouses are heated geothermally, but the greenhouses, the only energy demand is geothermal.
So diving into our water system, we are considering how conventional development for water and sanitation systems do not take into account the natural hydrologic cycle. And so we feel that people are disconnected from their water source. So with our design, we wanted to address questions of whether physical changes to water and sanitation systems can really influence changes in water usage patterns.
Right, so when we take a closer look at the map, we notice that only about a quarter of the land have been converted to farmland. So in comparison to the past 2 projects that we just saw, it's quite a bit smaller. So you may ask, how are we able to produce all the food for the community? So we do this by having a centralized food production strategy, a decentralized food production, and also by introducing novel or unconventional foods that we don't typically eat today. So first I'm going to focus on this building and the shining star of our central food production. And so this used to be a school in the community, and we're converting the ground floor to a cricket farm and processing plant. And so why crickets? So crickets have a very high protein content, and they also require a very small amount of food and feed and energy to grow these crickets. And so these are being farmed in lots of companies throughout the world, and one of them is this company called Intomo Farm in Ontario. And so that's what Michael has just passed around. They come in flower shape that we've actually baked into some banana bread, so come by our booth and we're going to try them afterwards.
So solar PV is going to be integrated into the community with building integrated panels on the south-facing roof of each of the houses. So you can see this diagram here. This is a typical retrofitted house. We have 250 watt panels for a total of about 12,500 kilowatts in our community. So also what you can see in the diagram are 2 10 kilowatt batteries. There's going to be 2 of these in each of the houses. And this will provide up to 5 days of autonomy from solar if we maintain a relatively reasonable baseline of wind, which based on our climatic data analysis is manageable. And if not, if both resources aren't there, they provide up to 2 days of autonomy.
The challenge we've been given is to retrofit a very typical Canadian suburban neighborhood made up of mainly single-family, low-density homes and low-rise apartment buildings with a few larger complexes scattered throughout it into an autonomous neighborhood. This community will be autonomous in food, energy, and water, that we will reuse as much of the existing built environment as possible while meeting our needs. So I'll just point that out on the plan. All of the housing stock that exists in our vision is retrofitted of what exists currently right now. We did have to remove a bunch for our agricultural land, but otherwise we wanted to completely recycle or reuse waste. And we also wanted it to be a socially cohesive community, incorporating shared and collective systems, collective responsibilities, for for example, in farming, childcare, etc., a shared economy, and collective ownership of property and resources.
Here we can see some of the crops that were chosen to be grown in our community, and we chose these crops based on high yields, high nutritional value, and also very importantly, crops that can be grown the longest outside in the Montreal climate. So the total caloric demand is the line that you see above, and that was our goal. So we had to make sure that each month we were meeting that, we were meeting those needs.
This is a graph of the domestic water use, and it shows that for every month there is enough rainfall water collection and monthly surplus, so that each of the months the water use is allotted for. And this shows the agricultural water use demand and collection. And as you can see, the demand is always below the amount of water we have. There are some months where it's pretty tight, so you have almost exactly the amount of water needed. But there's always enough water, whether it's from gray water, from the surplus from the domestic water that gets sent to agriculture, or from rainfall.
And for our heating strategy, we have two main systems. So first, we're using geothermal. There's going to be ground source heat pumps installed at each dwelling, and these will provide for the majority of the heating needs for our community. We're also going to have a solar thermal storage system. This is modeled after the Drake Landing community in Okotoks, Alberta. And basically how this works is that we're going to have solar thermal collectors on the roofs. And these will store heat from the summer in the ground for the winter. So there's going to be 228 boreholes. And by doing this, we're able to harness energy from like the warmer summer months and use that energy for the winter when the climate gets harsher. This is just a